let's move on to the second talk of today. We are very happy to have Bowen Shi, who is a graduate student at Ohio State University, and he will be a UQM postdoc next year at UC San Diego.
Yes.
Bowen, go ahead.
Oh, yes. Right. So this is my talk. I'll take half an hour. Right. So, okay. So, okay, my talk is a fusion rule from entanglement. So it's based on work which is already on arXiv last year. Okay. So this is the outline of my talk. Here's a motivation and introduction. And for our framework, we start from introducing our axioms, which are based on some local entropic conditions on the quantum 2D quantum state. And then we introduce a concept called information convex set. And from there, we derive the axioms, the theory of anyon, just from every law given a quantum state. So I'll introduce you about how to define the superselection sectors, in other words, anyon types, and the fusion multiplicities, consistency conditions on the multiplicities, and the topological entanglement. And finally, there's a summary and outlook. Yeah, please feel free to interrupt me at any time with questions. Okay, so our motivation is about it's a physical system, many-body physical systems. Our focus is on 2D gap phase. So we know that there's in 2D gap phase, or more generically, many-body systems, there can be emergent phenomena. So in 2D gap phase, especially there's things like fractional quantum Hall and quantum spin liquid. There's a non-trivial quasi-particle and properties emerge like anyons and topological order. So the key point is that it's come from interacting system, and symmetry is not essential. So then for the physical laws of anyons, currently there's you can look at the Kitaev's appendix. There is a theory called algebraic theory of anyon. It's proposed to be a general theory describing the gradient fusion of anyons, both abelian and non-abelian. That's believed to be the most generic thing. Sometimes it's referred to as a TQFT, or unitary modular tensor category. For condensed matter people, when they mention about this, they basically mean the same thing. So, for 2D gap phase, this is all about classifying quantum phase. So currently there is a well-accepted conjecture for 2D gap system as a unitary modular tensor category, and C-, which is a chiral central charge, classifies the bosonic gap phase without symmetries. Okay, so what is unitary modular tensor category? Basically, it tells you a lot of things. So given you a gap system, 2D gap system, because of interaction, the classification is not simple. It's just not an integer. Rather, there's a lot of things. First, you need to tell people about what's the superselection sectors. In other words, what are the anyon types? If there's no anyon, then you get a vacuum. If there's a anyons on the system, then you get multiple labels, 1, A, B, C. Okay, so if you take two anyons, you can fuse them. But abelian anyon theory is simple, but in general, you get a set of integers n, a, b, c. So that means if you put two anyon a and b together, it looks like, in general, a superposition of them. Well, they can have multiple fusion result, and for each result, there can be some non-trivial integers. And NABC satisfies some non-trivial conditions, and from NABC, you can actually uniquely determine what people call as quantum dimension, and the total quantum dimension, which count the total amount of anyons. Okay, so this is part of the theory, and more generally, you need to consider the modular matrices like S and T, and F and R symbol. There's consistency condition for the theory, and there is something called modularity that S is unitary for bosonic theory. Okay, our goal is to try to, let's see. So so for 2D, at this moment, this conjecture looks pretty good. and it's pretty well accepted for obvious reason. All the fields seem to agree with this. For 3D, the analog of this unitary modular tensor category and chiral central charge, the theory was the 3D analog of this. This is something people expect this to be related to 3D TQFT, but both of these are not classified, so it's kind of not completely known. And in 3D, people also know something beyond the liquid phase, like fractals. So So we ask the following question: can we provide a concrete framework for anyon theory to emerge? So if we can do this, then we can, in some sense, explain why the modular tensor category and chiral central charge should be the right description for the interacting depth of phase. So what we want is to start from something physically well motivated for 2D gap of phase, and one without symmetry. Okay, and we want the assumption to be general enough so that you can cover a large class of phase, hopefully all of them. Okay, and we want the assumption to be strong enough so we can actually derive natural predictions. Our framework is a recent attempt. So what do we do? Here are some hints about what we want to do. So works tells us many body ground state may potentially contain many information about the universal data. And for gap phase, there's something called entanglement area law. And if we use entanglement, then there's all kinds of results from quantum information theory, which we can use. Like the most famous one is strong subadditivity. That's linear combination of the entropy is always greater or equal to 0 for any quantum state. Okay, so so our intuition will be from the here is a conjectured form of entanglement area law. So for a subsystem of 2D a 2D quantum system, gap the 2D quantum system is alpha L minus gamma. So alpha L is the boundary of the subsystem A, but can be a constant gamma. So that's the area law. Basically, the intuition of the proportion to the length of the boundary is that for gap system, there's only local degree nearby. They can be entangled, but there can be some gamma, which they call topological entanglement entropy. For theory with anyons, it has been multiple ways to derive this famous relation gamma equal to log total quantum dimension. So so it actually ground states reveals some information about anyon theory, although it's partial information. So with these two original papers, Kitaev paper, they use this linear combination to, both of the linear combination are used to cancel out the linear piece so you can get gamma. So the universal constant. So Kitaev paper, they derive this result from topological quantum field theory assumption, and the level 1 paper, they derive this relation from the string net model. So they have exactly solved the model. So we want to take assumption, just use something related to entanglement, so which is the two axiom we will introduce very soon. So from there, we can actually recover this relation together with the fusion rules. So what are the axioms? So here is a quick look of our axioms. Well, so first we actually also take the axioms from the quantum mechanics. So basically, you can find them in any quantum information books. So it's the Hilbert space, the total Hilbert space. We will assume that to be a tensor product of a local Hilbert space. So each local Hilbert space is finite dimensional. So in addition to that, we propose two conditions, A0 and A1. Actually, it's quite amazing that my collaborator has considered these two conditions a few years ago. Actually, he was trying to derive the theory of anyon. He didn't show his we actually recently made progress. So yeah, I should point out those two conditions just follow from the area law. So we don't really assume more things than the conjectured area law. So let's take a look. As BC, so the B and C are subsystem on a 2D system. BC is a large disk, so it has one boundary. C is a small disk, it has one boundary. So B is an annular, so it has both of the boundaries. That's why, because of the area law, this thing actually cancels, you get 0. Yeah, the same reason for A1. So this linear combination SBC plus SCD minus SB minus SD is 0. Okay. So more precisely, what we do is we take just local disk. So your 2D system can be very large, but we just require the conditions to be satisfied on relatively small disk. So the disk will be larger than the correlation links, so non-universal things will decay to 0. We actually assume it's exactly 0. But the disk can be much smaller than the system size. So those are bounded radius disk from the reference disk side. So physically, this is we can assume this to be the ground state of a 2D gapped phase, like a topological order. Let's play with the axiom. So what it tells us, right? So we only assume those on a small disk. So here in this diagram, BC is small, so A can be large. So although it can be large, the axiom can actually tells us something about the entropy involved ABC. So the conditional mutual information defined like this. This linear combination is give you 0 on the ground state. Yeah, for the proof, we just use A1. This condition under the strong subjectivity, actually you can derive this conditional mutual information is 0. That says the ground state is a quantum Markov state. So intuitively, we can think of, we actually topologically deform BC into ABC. So there's some sense of topological deformation actually implied by the axiom. Okay, so let's go on. So we need some structure out of the quantum state. So here is a key concept, which is called the information convex set. So it's a convex set of dissymmetrices. We specify a subsystem omega which we want to care about. It can be of any topology, and we consider the thickening omega prime, which is an omega plus an extra layer around it. So first on omega prime, we collect some dissymmetrices on omega prime, which are locally indistinguishable from the reference state or the ground state. Then we do a partial trace for each of the real omega prime, then we get a set of dissymmetrices real omega supported on omega. This is a convex set, always a convex set. So the question is, can we will use quantum information theory to constrain the structure of those convex sets and then define the anyon theory from those structures. Okay. Any questions so far? Okay, so here is the main result, an overview of the main result.
I have a quick question here.
Okay.
In your previous slide, what is the operation under which this set forms a convex set? It's just I mean, these have different Hilberts. They act on different Hilbert spaces, right?
Oh, well, once you specify omega, the Hilbert space is fixed. Okay. So for each omega, we define a convex set of dissymmetrices.
And their convex set means, linear superposition with positive coefficient? Or?
Linear combination with a positive coefficient, and there is one additional constraint, that's the sum of coefficients equal to 1.
Okay, thanks.
Okay, all right, so from that, so we literally introduce all of our axiom and concepts, then we go ahead to derive these things. So we will derive something called isomorphism theorem, which is I'll tell you soon. So then we define topological chart and fusion rules. We derive the axioms about fusion rules, some consistency conditions, and the well-defined of antiparticles. We also rederive the topological entanglement entropy, and we will find that there's always some deformable unitary string operator that can create anyons. All right, so what's the isomorphism theorem? It says the following thing. It's quite intuitive. So you get omega 0 a subsystem, another subsystem omega 1, if those two can be related by a path, which is a sequence of a small deformation, then the information convex set are isomorphic. Okay, so so the isomorphism theorem preserves the entropy difference and fidelity, some measure of the distance of two elements. This will be important. Okay, so here is the sketch of the proof. So you have ABC, and you can locally deform the region AB from ABC to ABCD, and you can do a partial trace to come back. So this is and you can do a sequence of a small extension and a partial trace to move from omega 0 to omega 1. Yeah, that's the intuition. Okay.
I still have a question about this convex set. So what is the physical statement? Is it to say that a linear combination of density matrices which obey areal law gives rise to, another density matrix which obey areal law? What is the condition?
Oh, well, so...
What is the property of this set? Let me ask it this way.
Well, each of them can be, they locally minimize energy, right? And so suppose you have a local Hamiltonian, right? So suppose the reference state is the ground state. Then each element in the set in sigma omega, those are locally indistinguishable from the ground state. So you see this is actually a low energy state for some 2D gapped Hamiltonian. Then physically, you can expect this must have area law, right? It cannot be volume law. Because it's minimized energy.
Right. So my question is whether, is it obvious that any linear combination of areal law density matrices give an areal law?
Well, if the set is small, actually there is a way to do that. So, so you can consider, you can actually calculate the von Neumann entropy of the convex combination. If you have a convex combination of density matrices, there is a formula. Or you can give it an upper bound. It's actually not much more than each of the elements. Yeah, it slightly increased the entropy, but it's a finite amount actually. We will see some of this.
Okay, yeah, I just wanted to understand if this physical intuition. All right.
That's right. Yeah, good question. Yeah, let me, when we get there, I'll quantitate to you. Okay, so this is the isomorphism theorem. So with this, we can, so what's the next statement? The next one is about topological chart. So the idea is for x is annulus. For annulus x, the information convex set actually captures the topological chart in the following way. You can prove a theorem says this for the sigma x is always a simplex. Simplex is it has a isolated extreme points. We can label them. One is a vacuum, some other, you can label them. The labels will be identified to the anyon types. We will, later on, we will further establish the existence of antiparticle and the topological piece of contribution in the entanglement, but this comes later, okay. So how do we prove the simplex theorem? So this is because first, the annulus is a very special topology. You can divide this into senior for annuli, so L, M, and R. Okay, so because of the isomorphism theorem, the information convex set are identical, isomorphic for those choices of subsystem. We can consider something called fidelity, which involves two dense matrices. This fidelity is preserved under the isomorphism. Okay, so we have this. We take two elements in the information convex set, and the F, L, R, and the whole system, they are the same. Okay. Fidelity has a nice property that after you do a partial trace, it can only increase, not decrease. Well, this is quite intuitive because fidelity count measures the overlap between two states. Two states can only have more overlap on a smaller region on a subsystem. Okay, so the third one is harder, but actually you can show for extreme point. If you take rho and sigma to be two extreme points, then the fidelity actually decomposes because each of the states rho and sigma are tensor products on L and R. With those equations, you can actually show f is smaller than f squared, but fidelity is something between 0 and 1. There's just two solutions. Either you have f equal to 0 or f equal to 1. So f equal to 0 actually means rho and sigma are orthogonal. F equal to 1 if and only if rho and sigma are identical, they are the same. So then if you have two different extreme points, it must be orthogonal. Then because we assume that the Hilbert space is finite dimensional, there can only be finite number of orthogonal extreme points. So we always get a simplex. So any questions about the proof? Okay. Yeah, so it's a simplex. We can define the anyons with the extreme points. Okay. Then how about fusion rules? We can just take a different topology. Here is a two-hole disk, a disk with two holes. Okay. So because it has subsystems, so we can take subsystem around each entanglement cut. And we have started the information convex set for annulus. So we know that we can label A, B, and C on each entanglement cut. So then you can ask, once we specify A, B, and C, are there any other degree of freedom? It turns out, yeah, we can prove the following. So we take sigma A, B, C, Y is the subset with the fixed anyon types on the entanglement cut. You can show that those things is isomorphic to a set of dense matrices on a finite dimensional Hilbert space. It's always correspond to a single Hilbert space with determined by n ABC. So yeah, so naturally there's one coefficient ABC. So physically that means this thing can potentially store a piece of quantum information through the NABC coefficient if it's greater or equal to 2. Okay, so yeah, I can sketch you the proof. It's a bit complicated, but I can mention that axiom A0 is useful in showing the coherence. Okay, so now we have anyon types and fusion rules then, but the multiplicity are not just non-negative integers, they satisfy a set of rules. There's 1, 2, 3, 4, 5. We want to show them as well, and yes, we are able to show that. So the first one is intuitive. We just do a rotation with the isomorphism theorem. The second one is also intuitive with a chart. Okay, N1 AC means in the 3 entanglement cart we have 1 A and C. The one with the vacuum is the reduced matrices of the ground state. So we can just merge a disk. So you see it become the annulus. Then A and C must be the same, otherwise, or it's an empty set. So we get delta AC. And the next 3 is more counterintuitive, at least in for the first time you see the proof. So I should mention to you that there is a new technique. So we need the following. We need to calculate the entropy difference and compare the entropy difference. There's some consistency we can consider. Okay, so we can first define the entropy difference. Fa is the entropy difference between 2 extreme points. divided by 2. So first it's universal because of the isomorphism theorem. Okay. So there is something called merging technique. That's the following. So start from two quantum Markov states. That's the state with vanishing conditional mutual information. We can actually merge them to get a new quantum state on a larger subsystem. And yeah, this process preserves entropy difference. And the new state is a quantum Markov state. And yeah, we are also able to show that if we start from states in the information convex sets, the result is also in the information convex set. Okay, so let's use this. In order to derive 3, we can merge charge 1 and A in the following way. So on the left-hand side, okay, we actually compare merge of 1A and 1,1. So the entropy difference from the left-hand side is 2FA, because that's the definition of FA. On the right-hand side, so yeah, well, what we can tell is we have charge A in this hole and 1 in the outermost entanglement cut. So how about this hole? In general, it may be a superposition of B, and we also know that the merged state is a maximal entropy state with a charge 1 and A. So in order to maximize the entropy, we need the following. So with the strategy is to get all the possible choices of B and do a superposition. So in this way we maximize the entropy. Okay. So right. So from this we can actually find this formula, and it actually implies that first FA is always greater or equal to FB, and also we have the FB greater or equal to FA because of the symmetry. And it turns out that this is a very strong constraint. For this to be true, we must have a unique A bar for each A. So each time we have only one choices of A bar to satisfy the following. So there's only one way to fuse into A bar, and the entropy are the same. So yeah, this actually defines the antiparticle. Okay. So yeah, for condition 4 and 5, the idea are quite similar. Yeah, we skip them because of the time. Right. So okay, now yeah, let me show you the derivation of this formula, topological entanglement. Yeah, let's take the level 1 partition. So first we can show that the topological piece of entropy is log FA by the following merging. Again, we compare the entropy in 2 different ways, on the left and on the right. Then 2 different results need to be consistent. Then it leads to this equation, and this equation only has one solution. That's e to the FA equal to the quantum dimension. Yeah, so we get this result. And by the merging, we know that in the information convex set, there is an element with a vanishing conditional mutual information. So in this way, we can replace some of the terms in the original definition. Then it turns out the topological entanglement twice of gamma will become the entropy difference between the center and the corner. So here, the center and the corner has some entropy difference. The one in the center has some additional entanglement. So Hassan, this comes to your question. I can explain this part to you. In the one in the center, how do you get that? You get you can just do a linear, a convex combination of all the extreme points. There's some probability involved in the superposition. Then you maximize the coefficient, the probability distribution. Then you get the maximum entropy. This calculation is actually easy because all the extreme points are orthogonal. Okay.
Yeah, I see. Thanks.
Yeah, you're welcome. All right, so yeah, so I want to I think it's almost that time, so I'll go slightly faster. So, yeah, we can, right now it's about fusion rule, then you can ask whether the same axiom actually imply further things. So I'll show you one thing. So this is about string operator. There's an intuition, like if you know Turing code, then you know that each anyons can be created by a string operator. We are actually, yeah, from not building models, a string operator are harder, but they exist. We can actually show that. So because we have density matrices, density matrices can help us to determine the support of string operator. Yeah, actually able to show for each anyon there is a deform of a unitary string operator. Okay, yeah, we have done enough for the derivation. Let's come back to the philosophy of our work and do the summary. So the summary is the following. It's a very clear picture of what we are trying to do. We think that entanglement actually provides a concrete mechanism for the law of anyon to emerge. So a quantum state, a 2D quantum state, well, with the error law, if they satisfy A0 and A1, we are able to show the following. We have two output. If you give me a state satisfies the axioms, we can show you the following. First, the anyon theory about the length scale involved in the axiom. So right now it's a part of the anyon theory, so I'm saying it's in progress. And anyon data is contained in the disk region of the ground state. So if you look at our strategy, you find that we only require some subsystem, so it's part of the whole system. We didn't really use the global data like with topology, the manifold 8. We just use a region which is large enough than the correlation lengths. Then we are able to, in principle, we can extract the data. And yeah, here is some outlook. So obvious directions are like the other modular matrices, S matrices, has been extracted. And we are trying to extract F and R. Here's some method which may help us. We found a recent paper there use string operator to define F and R. And because we have string operator, we think the strategy work for us. And another question is, can we extract chiral central charge with our framework? Currently, it's not obvious to us, but I think it's a fair question, right? And for fermionic models, some setup or axiom has to be modified. And we can also go beyond anyon theory, like obvious direction are like get a domain wall. That's the interface between two topological faces in 2D. And we can also consider 3D. Yeah, it's actually the axiom are straightforwardly generalized in this situation, and we can make predictions that's not trivial. Okay, and third, yeah, I need to say that up to now we require some exactly satisfied axioms. Then the question is, can we generalize like from a quantum state which related to the exactly satisfied area law state with a finite depth circuit? We can actually, we think we can generalize. There's some progress, and approximately satisfied axiom. This right now we couldn't say very concrete, but there's some tools available for approximate quantum Markov states. There's a theorem from Quantum Information Society, so people may try to use them to generalize. And so how about the RG flow? Here is a very interesting question. At least I find it interesting because, well, there's the two axioms satisfied. Yeah, we'll assume the two axioms. And there's some breakdown of one of them is called A1. Anyway, but also there's important counterexamples are actually above the threshold of log 2. It looks like the violation of axioms are quantized. And the question is whether if you start from a quantum state with violation smaller than log 2, is it always run into a smaller number at large length scale? So that I think it's interesting because currently the area law is kind of a conjecture. If for people who are careful with that, so I think maybe we can make some progress to justify area law better, then we know better about the range of validity of our framework. So thank you.
Thank you so much, Bowen. I have one quick question.
Yeah.
So is it easy to incorporate symmetries either in context of like symmetry protected topological phases or symmetry enriched topological phases here?
So yeah, for symmetry enriched, I think the answer is yes. So we will have information convex set. So actually, if you have a let's say an onset global symmetry, then you actually do it can act on the elements in the information convex set. Typically, it will map one extreme point to another. You can also consider to doing it on a two-hole disk or something. I think there is something people can say about that. And for SPT, bosonic SPT, I don't think there's an interesting structure because those things depend on long range. There's a local indistinguishable state which are non-trivial, but for fermatic one, maybe there's something like Kitaev chain, but the definition need to be changed. There's modification. Yeah, I'm actually thinking about the fermatic problem recently. I don't think it's trivial. I'm struggling with what assumption to take, but there's a different way to go, but I find none of them are straightforward. It's an interesting question.
Right. Yeah, I guess like you said, you need to find an operator which maps maybe one element to another in your convex set. Yeah, I guess it's maybe it's easier to work with like SET, which gives you like G crossed UMTC. I don't know. Maybe you can derive that. Yeah. All right. Yeah. Thank you so much. So we have time for more questions, comments. All right. If there is no more question, this session is concluded. And I have just one quick announcement to make. So we are actively looking for volunteers to give talks, this 30-minute format talk, as you know, we have been doing it so far. So I prepared a Google Doc, so you can put, there are like empty spots on it, and you can write your name if the timing works for you. I will share that Google Doc soon. And with that, I guess we're done. And let's thank both speakers again, Ruben and Bowen. All right, so have a good day, everyone. Thank you.